Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll look at learning outcome A from the topic of theories of acids and bases from the JCH2 chemistry syllabus. Specifically, learning outcome A states that candidates should be able to show understanding of and apply the Arrhenius theory of acids and bases. So as we discuss any theory, we always start off by defining the terms that we are interested in discussing in that topic. So for example, if we were studying a topic of kinematics from physics, we will always start by defining displacement, velocities, and acceleration. So if we are discussing the theories of acids and bases, we will start off by defining acids and bases. In fact, in this chapter, all we are interested in really is the three different types of definitions of acids and bases, specifically the Arrhenius definition of acids and bases, the Bronsted-Lowry theory of definition of acids and bases, as well as the Lewis definition of acids and bases. I will talk a bit on why there exist three different types of definitions as we move along in this topic. So let's begin with the Arrhenius definition of acids and bases. So in 1884, Arrhenius proposed the following definitions for acids and bases. He defined acids as substances which produces the H plus ions in solution. And he also defined bases to be substances which produce hydroxide ions in solution. So let's look at an example of an Arrhenius acid. So when a substance like HCl gas dissolves in water, a dative covalent bond is formed between one of the lone pairs on the oxygen of water with the H plus on HCl. So for those of you all that are familiar with reaction mechanism, this is the schematic mechanism of the reaction. If you're not familiar with this, don't worry about it. We will do more of this when we come to organic chemistry. So basically, the oxygen has two lone pairs. It will use one of the lone pair to form a dative covalent bond with the hydrogen of HCl, pulling out the H, or specifically the H plus from HCl, and you will form the H3O plus cation and the Cl minus N ion as shown in this reaction. So HCl gas dissolves in water to form the H3O plus cation in solution, as well as the Cl minus N ion in solution. This may not be familiar to some students as it has been commonly simplified as the following equation. So the HCl gas simply dissolves to form the H plus cation and the Cl minus N ion. But in reality, in solution, the H plus cation is actually the simplified version of the H3O plus cation. Now at the A level, it is both acceptable to write this equation or this equation. And depending on which is more convenient, we will actually choose which equation to write. But what I would like to point out here, the important thing is that don't be confused. Basically, the commonly written H plus cation of the acid is in actual fact the H3O plus ion. They are actually equivalent species. And since HCl gas dissolves in solution to form the H plus cation, it certainly qualifies as an Arrhenius acid. So basically, if you like to check if whether it's something an acid, you go back to the definition. Right? If the definition says that there are substances which produce H plus ion in solution, you ask the question, does it produce H plus ion when dissolved in solution? If the answer is yes, it's an Arrhenius acid. If the answer is no, it will not be an Arrhenius acid. As simple as that. And that's the reason why we always start with definition, because it forms the foundation of any theory. When we want to discuss something, whether it's true or not true, you always just go back to the definition as you have a fallback to discuss on whether it's right or wrong. Okay, so that's an example of an Arrhenius acid, basically the HCl gas. Now let's look at an example of an Arrhenius base. When a substance like NaOH solid dissolves in water, the NaOH solid will dissociate to form the Na plus cation and the OH minus anion. So the NaOH solid dissolves in water to form the NaOH aqueous solution, which is equivalently the Na plus cation and the OH minus N ion, because these ions are basically freely moving around within the solution. And since the NaOH dissolves in solution to produce OH minus ion, it qualifies as an Arrhenius base. Let's talk about a reaction of Arrhenius acids and bases, and that reaction is called neutralization. Neutralization specifically is when the H plus ion and OH minus ions in solution react to produce water. So the simplified version would be just the H plus cation reacting with the OH minus N ion to produce water, or the most sophisticated and more accurate version, in fact, the H3O plus cation reacting with the OH minus anion to form water. So this is known as the neutralization reaction. A specific example, hydrochloric acid reacting with sodium hydroxide to form sodium chloride salt and water. So the H plus ions from HCl aqueous will react with the OH minus ions from the NaOH aqueous to produce water. So, and this reaction is consistent with the Arrhenius definition of acids and bases because the HCl aqueous produces H plus ion, while the NaOH aqueous produces OH minus ions in solution. Another example, aqueous ammonia. When aqueous ammonia dissolves in water, it will actually undergo this reaction whereby it will form the NH4 plus cation and the OH minus anion. And since it dissolves in water to produce OH minus anion, this is an Arrhenius base. So basically aqueous ammonia is an Arrhenius base. And of course, if you react HCl aqueous, hydrochloric acid, with aqueous ammonia, you're going to form the salt NH4Cl and water, which is a neutralization reaction again. And this reaction is again consistent with the Arrhenius definition of acids and bases, since HCl dissolves to form H plus ion, and the aqueous ammonia dissolves in water to form OH minus ions, which then reacts to form water. So this reaction is also consistent with the Arrhenius definition of acids and bases. However, what happens when when gaseous ammonia reacts with hydrochloric, not acid, sorry, HCl gas in the gaseous phase? So now there is no solution, right? So basically, NH3 will not be able to form OH minus ion, and HCl will not be able to form H plus gas. And however, it is actually still true that they will react to form NH4Cl salt, right? So this reaction between the reactants in the gaseous state is very similar to that in the aqueous state, because like if you were to compare this reaction with this reaction, right, you can see that with the exception of the water and no water is produced, right, the reaction produces the same product, right? So they're very, very similar. And it's a bit strange if we were to say that in solution, this is an acid-base reaction, and in the gaseous phase, this is not an acid-base reaction, because this is essentially really the same reaction, right? However, because there are no H plus and OH minus ions in solution, because there's no solution, right? So this reaction is inconsistent with the Arrhenius definition of acids and bases. So why are we discussing this? Basically, this is a precursor for the next learning outcome, why we would like to have another definition of acids and bases, which would then be able to cover this reaction as an acid-base reaction. Okay, so let me repeat once more. This reaction is inconsistent with the Arrhenius definition of acids and bases. So we would like to seek a new definition, which is actually broader, which will also allow us to classify this reaction as an acid-base reaction. And that will be the definition of the Bronston-Lowry definition of acids and bases, which we'll discuss in the next learning outcome. Okay, so basically let's wrap up this video. So basically learning outcome A is to show understanding of and apply the Arrhenius theory of acids and bases. Basically this definition that Arrhenius acids are substances which produce H plus ions in solution, while Arrhenius bases are substances which produce hydroxide ions in solution. And I hope now you are now able to learn, answer this learning outcome. Okay, so thank you for watching this video. If you like this video, please hit the like and subscribe button. And stay tuned, and I'll see you for another video by Einstein Academy as we discuss the Bronston-Lowry theory of acids and bases.